Hello, dear students. How are you? I hope you all of you are doing good and having great health. So today we are going to discuss this chapter in a crash course format, KTG and thermodynamics. It's a very important chapter by the point of view of this JEE examination, and I hope this lecture would help you a lot. As according to the format, firstly we will going to see the concept and then we will solve the PYQ based on that. Now, in KTG and thermodynamics, the most of the part of this chapter is, we can say that 60% of the portion of this chapter is theoretical and 40% of this is numerical based. Now, the very first thing here is the laws. So the very first law here is Charles' law and Boyle's law. We usually have the understanding of these laws from the previous classes. So Charles' law at constant temperature is nothing but that volume is directly proportional to temperature. But for that, you need to keep in mind that constant pressure is the required condition. So volume will become directly proportional to temperature. Further, we can write it as for two process V1 by V2 equals to T1 by T2, and similarly we can do that. Now, the Boyle's law here is the same, but here we have to keep the temperature as constant. So at constant temperature, pressure is directly proportional to 1 by V. So we can say pressure and volume as an inverse relation. As you increase the volume, pressure will decrease, and if you decrease the volume, the pressure will increase. Ultimately, we can also write it like this: P1 V1 equals to P2 V2. Now here, it is the key concept, or you can say the bonus concept, is that mean free path. So mean free path is equals to 1 upon root 2 n pi d square. Now, where n is the number density, which is number of molecules per second, and d is the diameter of a molecule. D is the diameter of molecule. Now, what is the mean free path? Suppose we have two molecules. So this molecule, how much distance it traveled to have the collision in between. So mean free path is nothing but the distance traveled by the molecule, or basically the average distance traveled by the molecule in successive collision, the collision one after another. Now, Gay-Lussac's law and Graham's law. Now, Gay-Lussac law says that for a given mass and constant volume, pressure is directly proportional to temperature. As you increase the pressure, temperature is increased. So this is for a given mass, which means mass we have to keep as constant and constant volume. This is P1 V1 by P2 V2. This is the Gay-Lussac law. And Graham's law is nothing but it's about the rate of diffusion. It's about the releasing of the gas. So at constant pressure and temperature, the rate of diffusion is directly proportional to 1 upon square root of density, which means R is directly proportional to square root of 2. Now here you can notice one thing. If you increase the density, the rate of diffusion will decrease, which means what? If a gas having very large density, the rate of diffusion for that gas will be very low, which means heavier the gas, uh, longer will be the time to spread it. Okay? So that is the key factor. Now, ideal gas equation, if you take the Boyle's law, Charles' law, and Graham's law, and this Gay-Lussac law, P is directly proportional to V, P is directly proportional to T, sorry, not V. P is directly proportional to 1 by V, P is directly proportional to T. So if you just combine this law, you will get P is directly proportional to T by V, and you can say that PV is directly proportional to T. Now, if you just remove this proportionality sign, PV will become NR into T. This N is the number of moles here, and R is the universal gas constant. And this equation is nothing but the ideal gas equation. PV is equals to NR, where P is the pressure, V is the volume, N is the number of moles, R is the universal gas constant, and T is the temperature. Now, one of the best formula for R is to remember this. R is equals to Kb into Na. Now, where Kb is nothing but the Boltzmann constant. It's the Boltzmann constant. And Na is the Avogadro's number. Avogadro number. Avogadro number has a value of 6.023, 10 raised to the power 23 molecules. Okay. And it is also the number of molecules in the 1 mole of gas. Now, the very important theory, which is kinetic theory of gases. So there are the assumptions that are really important for a assertion reason type of question or true false question. A gas consists of large number of identical tiny spherical neutral and elastic particles called molecules. This is the first postulate, which means whatever we identify as a molecule is the identical for if I'm taking a gas. So in that gas, two molecules are identical to each other. They are very tiny, spherical, neutral, which means they do not have any charge contained, and elastic particle, which means they can on the collision they can have a elastic property show. In a gas, molecules moves in a all possible direction with all possible speeds. So which we can that gas molecules have random motion. The third thing here is the space occupied by the molecules is much smaller than the volume of gas. Although this assumption get nullified or get rejected when we see the van der Waals equation, gas equation, or van der Waals correction. The space occupied by the molecules is much smaller than the volume of gas. There is no force of attraction among the molecules. Okay, this is also really very important. The pressure of the gas is due to elastic collision. The pressure of the gas due to elastic collision of a gas molecule with the walls of the container. So pressure का जो definition we have studied, the pressure is force per unit area. That force is coming when a molecule hit the walls and move back. So in this collision, it is exerting force on the wall of the this container, and this force per unit area is nothing but the pressure. Got it? Now, the time of contact of a moving molecules with the walls of the container is negligible as compared to the time interval between two successive collision on the same wall of the container, which means whenever they are colliding, the time spent in the collision is negligible, but time spent to travel to have the collision is something that we cannot ignore. Okay. Now, the next thing is pressure, and that pressure is concept of pressure, which we have seen in the previous postulate. Pressure is the only factor that will be developed due to the elastic collision of the molecules with the walls of the container. That is the pressure. Now, if we have the derivation, we are skipping it because it's a crash course, so we are skipping that. So pressure will become 1 by 3 times Nm V bar square, where N is the number of molecules m is the mass of one molecule, and v bar square is the average velocity of a molecule ka square. Now, this is the another formula for that. It's 1 by 3 m by v, which is the mass, molecular mass upon volume of the gas multiply by velocity square. Now, this you can also write as mass per unit volume is density. So 1 by 3 rho v square. This is also you can write it. This is the pressure. Now, based on that, we have the three velocities here by which a molecule can move in a gas container. First velocity is the RMS velocity, which is nothing but square root of 3 kBt upon m. This small m, you have to pay attention. This small m here is the mass of one molecule. Mass of one molecule. And this capital M is the molecular mass, which means the mass of the particular molecule at 1 mole. Whatever the mass a gas or any particular substance contain at 1 mole is the molecular weight of that. Okay. V average here is the 8 RT upon pi m. So this you need to remember. This coefficient, temperature will be same in all the three velocities, but this coefficient is changing. So Vrms is 3 RT upon m. V average is 8 RT upon pi m, which we further can write as 8 kBt upon pi, where kb is the Boltzmann constant. And Vmp, which is nothing but the most probable speed, which means the speed by which most of the molecules of the gas are moving. That is the most probable speed, is equals to square root of 2 RT, which is equals to square root of 2 kBt upon m. So we can say that velocity of any molecule or any velocity of a molecule, which is we can say Vrms, V average or Vmp, holding a relation inversely proportional to the mass and directly proportional to the temperature of the gas. Okay. This RT you can replace by PV, because we know that PV is equals to nRT. So this PV you can replace for 1 mole of gas. PV is equals to RT, which means in this formula you can replace it by PV. So it will be 8 PV upon pi m, and this V by m will become 1 upon rho, which is nothing but the density. So in terms of density also we can variate it. Now, the specific heat, capacities and concept of mixture. The specific heat capacity is nothing but the heat that we require to raise the temperature of a system by 1 unit of a unit mass. So that is the specific heat. And heat capacity itself is the specific heat capacity is the heat required to raise up the temperature by 1 degree Celsius for 1 unit mass, for a unit mass. But specific heat, heat capacity is the amount of heat required to raise up the temperature of any mass by 1 degree Celsius. So that is the difference in between them. Now, specific heat, specifically what we talk and what we should learn here, that specific heat is nothing but the thermal resistance of a metal. Suppose a particle require 100 joule of energy to raise the temperature by 1 degree Celsius, and another particle require 1000 joule of energy or 1000 joule of heat to raise the temperature by 1 degree Celsius. So in both the cases, you will see in both the cases, the amount of heat is increased, which means the same material, the material resisting this change of temperature up to 100 joules, but the another material is resisting the change of 1 degree Celsius by 1000 joules. So specifically, this specific heat capacity or the thermal resistance of the matter. We have two types of specific heat capacity. First is specific heat capacity at constant volume, which is nothing but the U, internal energy of the system, and this is for the ideal gas. U is equals to CV into delta T. and specifically we can say mCv delta T. Okay. Now, but if mass is 1 unit, then we can say U is equals to Cv delta T. Specific heat capacity at constant pressure is nothing but the heat supplied to the system, which will be given by Cp into delta. Now, these are some important formula based on that discussion. For monoatomic gas, degree of freedom of the gas will be 3. Now, what is degree of freedom? Degree of freedom is nothing but the how many ways a gas molecule can move or can change its state. Okay? Of motion, I am saying that. So suppose we have a monoatomic gas which will be given like a molecule. So it can only move in X, Y, and Z direction. So for monoatomic gas, degree of freedom will become 3. But if we take a diatomic gas, so for diatomic gas, let's say this is the structure of diatomic gas. So what we can say, it can move in X, Y, and Z. Along with that, it can also rotate about this axis and also rotate about the vertical axis. So 2 rotation plus 3 translational degree of freedom it has. So the degree of freedom for which for the diatomic gas will become 5. Got it? Now, for monoatomic gas, if degree of freedom is 3, the formula for Cv and Cp is 3 by 2 times of R and Cp will become 5 by 2 times of R. Now, if you just know the value of Cv, how to calculate Cp, that we will done with the help of Cp minus Cv is equals to R, which means Cp is equals to R plus Cv. ठीक है? R plus Cv, देखो, if Cv is 3 by 2 R, just add R into it, it will become 5 by 2 times of R. This gamma is nothing but the adiabatic constant or the ratio of specific heat at constant pressure to the specific heat at constant value. Now, for diatomic gas, degree of freedom is 5, I have told you. Cv will become 5 by 2 times of R. Cp will become 7 by 2 times of R. For any mixture, it will be N1CV1 plus N2CV2. N1 and N2 are the number of molecules of different gases. CV1 and CV2 are the molecules of, sorry, specific heat at constant volume for different gases divided by the total number of molecules. Gamma of any mixture is nothing but 1 plus 2 upon F of mixture. F is nothing but degree of freedom. And this formula you can learn. Okay. Now, here are some important points. The equipartition of just a second. Equipartition of equipartition of energy. So, according to kinetic theory and law of equipartition of energy, we can say that each and every molecule possess 1 by 2 times kb into T amount of energy for each degree of freedom. Okay. So if degree of freedom, this is for 1 degree of freedom. 1 degree of freedom. Okay. Now, this we can write for generalized way. If degree of freedom is, if degree of freedom is F for any particular gas, it must possess the total kinetic or total energy possessed by that gas is F by 2 into kb into T. Okay. So if a gas is possessing 3 degree of freedom, the total energy will be 3 by 2 kb into T, and that would be specifically kinetic energy of the gas, because in ideal gas, most of the molecule, or mostly we talk about the kinetic energy, because molecules are always in random motion. So this is but the translational kinetic energy, or we can say total energy possessed by a gas. Okay. Now, similarly, there are different kind of processes. We should learn about them. First is isochoric. Isochoric process. So isochoric process is nothing but the process that will be having constant volume. Volume will become constant. So for PV graph, it will be having constant volume, which means this. This type of variation of graph it will be possessing. Second process is isobaric process. Now, what is isobaric process? The process which contain or which will be having constant pressure. Here the pressure will be constant. So if the pressure is constant, the graph will be like this is P, this is V, so graph will become this. Okay, like this. So each and every time pressure is now sorry, this will be the isochoric, because each and every time pressure is increasing but the volume is constant, and this will become like this. For each and every time or each and every volume, the pressure is constant. Now, isothermal process. Isothermal process. So by the name of it, this process, we can say isothermal process is that in which temperature remain constant. So if temperature remain constant, the PV diagram will be written like this, like this. This is the graph for isothermal process. And there is another process, adiabatic process. Adiabatic process. Now, adiabatic process is nothing but in which there is no transfer of heat, which means we can say Q is constant. For that, the graph will be like looking like same, but it is steeper. It has, if this is having a slope, let's say 2, this will having a slope 4, which means the slope of adiabatic curve is greater than the slope of isothermal curve. Okay. Now, one more thing I want to have you with. This is the work done. Work done in thermodynamics. Work done we always write like P into change in volume, or for a specific process in which the pressure is not constant. So for that we will have P into dV. Now adiabatic process के लिए the process will be given like this: PV raised to the power gamma is equals to constant. Okay. The isothermal will be given by PV is equals to nRT, but temperature is constant, so it will be PV is equals to constant. This is for adiabatic. And this is for isothermal. Now there is another process also which is termed as polytropic process. Polytropic process. It is given by PV raised to the power n is equals to constant. So based on the value of n, we can define different process. Suppose if n is equals to gamma, so it will become PV raised to the power gamma, which is nothing but adiabatic. If n is equals to 1, it will become isothermal. If n equals to 0, then it will become pressure is equals to constant, which is nothing but the isobaric process. Okay. Now, first law of thermodynamics is that whatever the heat is given to a system, it will transfer to the change in internal energy of the system plus work done by the system or on the system. If the work is done on the system, that work will be taken as positive, and if work is done by the system, that will taken positive, and if work is done on the system, that will be taken negative. Got it? Or vice versa, whatever you want to take, you take. Okay. Now, but if you are taking work done on the system positive, then you have to take work done by the system negative. Okay, these types of symbol or the precaution with the sign you have to maintain. Okay. Now, the very first question here. Just try solving some questions. A mixture of 1 mole of monoatomic gas. देखो 1 mole है monoatomic gas है. Monoatomic gas. And 1 mole of diatomic gas. Okay. Are kept at room temperature. The ratio of specific heat of the gas at constant volume. Specific heat at constant volume is C. And for monatomic gas, it will be 3 by 2R. And for diatomic gas, and this is rigid. What do you mean by rigid? Rigid means that it is not vibrating. If it is non-rigid molecule, then it will vibrate. So 2 extra degree of freedom it will possess. But now it is rigid. So degree of freedom it will possess is 5. So it is 5 by 2 times of R. This is for mono and this is for dia. Now the ratio is been asking mono to dia. So this will be 3 by 2 multiply by 2 by 5. 2 and 2 will cancel out. So 3 by. So 3 by 5 is the answer. This is the main question. Okay. Now the pressure P and temperature T relationship of an ideal gas obeys equation Pt square is equals to constant. The volume expansion coefficient of the gas will be. Now, the process that is given to us is Pt square is equals to constant. Now, volume expansion coefficient is nothing but gamma, and we know the relationship that dV is equals to V into 1 plus gamma into delta T. Now, just multiply it inside, so it will become dV is equals to, or it is not dV, it will be the final volume. V final is equals to V initial into 1 plus gamma into delta T. This is delta V. Okay. So delta V को we can write as dV V 1 plus gamma dt. Now, if you just divide it with V, dV by V will become 1 plus gamma into dt. So gamma here is nothing but, if you see gamma, gamma will become, this is the V final. Just a second. जैसे हम टेम्परेचर का भी निकालते हैं, रेसिस्टिविटी का, तो रो इज इक्वल टू रो नॉट 1 + α ΔT। ठीक है। नाउ सिमिलरली दिस इज वी फाइनल is equals to V initial 1 plus gamma delta T. Now delta V is nothing but V final minus V initial. This is initial. So V final we have as V initial multiplied by V initial gamma delta T minus V initial. This and this will cancel out. So delta V ko we can write dV V gamma dt. So here gamma will become dV by dt into 1 upon V. Now so simply we have to calculate dV by dt. In this expression, if I put PV is equals to nRT, the pressure in terms of volume if I put here, it will be nRT upon V. Now put this expression here, differentiate it with respect to volume and temperature. So nRT upon V into T square will be constant. Now this nR is also a constant, so we can write T cube by V is equals to constant. Now just differentiate this expression with respect to temperature. So we can say that it is V something multiplied by constant equals to T3. So we can say dV by dt is equals to 3T square. Got it? And gamma is nothing but 1 upon V dV by dt. Put this here. Gamma will become 1 upon V into 3T square. Now, V can we write as, देखो, V will write as nRT upon P, और P का वैल्यू हमें गिवन ही है, समथिंग कांस्टेंट divided by T square. So 1 upon, I can write is constant upon T square. This will multiply up. So it is nothing but constant into T cube. ठीक है. So वॉल्यूम का वैल्यू कितना हुआ? 1 upon constant into T cube multiply by 3T square. So this T square will cancel out. So it will be 3 upon T. If I remove this constant, so it will be 3 by T. Now this one. A real gas, this is a real gas, within a closed chamber at 27 degrees Celsius undergoes the cyclic process as shown in figure. The gas obeys PV cube is equals to RT equation for the path A is equals to A to B. This path will be following the process PV cube is equals to RT. The net work done in the complete cycle. ठीक है. So here the cycle is, देखो cycle क्या है, A to B है, यानी AB, then BC and then CA. अभी AB को साइड में रखते हैं, BC और ACA के बाद. BC is nothing but a, देखो यहाँ पे क्या है, प्रेशर कांस्टेंट है, इट्स आइसोबारिक प्रोसेस, सो वी कैन से वर्क डन इज नथिंग बट P into डेल्टा V. और P क्या है यहाँ पे 10 है, एंड डेल्टा V कितना हुआ 4 माइनस फाइनल 2 है, V फाइनल माइनस V इनिशियल 2 माइनस 4 विच इज -20 जूल. तो आप देख सकते हो कि यहाँ पे वर्क डन नेगेटिव आया, विच मीन्स गैस कंप्रेस हुई. तो गैस को कंप्रेस किसने किया होगा, किसी आउटर सोर्स ने किया होगा. So this is the work done by the on the system. So that will be negative. Now CA, we having constant volume. So work done in this CA process is zero. Zero work done. Now this is remaining. Again we know, if we do not have any idea about the process or try to apply this formula PdV. Now P is nothing but written as RT upon V cube dV, and temperature is constant 27 degree. So we can say RT we can take common. It will be integration of V cube, which is nothing but minus 1 upon minus 2V square. Volume, the limits are 2 to 4. Because at A the process start, the volume is 2. At B the process end, the volume is so 2 to 4. Now R into T multiply by this minus 2 we can take common, so it is minus RT by 2. And this will become 1 upon 16 minus 1 upon 4, which is nothing but 12 upon 16 into 4 multiply by minus RT upon 2. And this minus will cancel out because ultimately this is also coming out as minus 12. Minus into minus will be plus. R ka value we have as 8. So we can put it as 8. So 8 to the 16. And 4 3 is a 12. So we having 3T upon 4. Now, if you take the temperature here, temperature you need to convert into absolute value, which is 300. 27 degree plus 273 will be 300. Now just multiply, it will become 75, which is nothing but 225. Okay, Joule. Now the total work done will be nothing but work done in AB plus work done in BC plus work done in C. अब CA तो 0 है, BC is -20 and AB is 225. So total work done will become 205 Joule. Option B is the correct one. Now this one. The temperature of a gas is -78 degrees Celsius and the average translational kinetic energy of its molecule is K. The temperature at which the average translational kinetic energy of the molecule of the same gas become 2K. I've told you what is the average translational kinetic energy is nothing but 3 by 2 kb into T. So directly proportional to temperature. This is kb. So we can say that K1 by K2 is nothing but T1 by T2. Simple सा बात है. K1 is K, K2 is 2K. Temperature T1 is -78 degrees Celsius. -78 plus 273 divided by T. Now K and K will cancel out. So temperature will become 2 times of -78 plus 273. And when you solve this, the answer is coming out as 117 degrees Celsius. This one. Got it? Now, this one. The volume of an ideal gas, the gamma is also given 1.5. The change is changed adiabatically from 5 liter to 4 liter. The ratio of initial pressure to the final pressure. This PV raised to the power gamma is equals to constant. This is the process for adiabatic. We can write it as P1 V1 raised to the power gamma equals to P2 V2 raised to the power gamma. Similarly, we can write P1 by P2 is nothing but V2 by V1 raised to the power gamma. Now, what is P1 and what is P2? We have to calculate that ratio, initial pressure to the final. So we kept it aside. Now, V2, which is the final, which is nothing but 4, and V1 is the initial, which is 5, given as 1.5. Now, just mathematics here, 1.5 we can write as 3 by 2. Now, distribute this power. So we can write 4 as 2 raised to the power 2. So 2 multiplied by 3 by 2 divided by 5 multiplied by 3. 5 raised to the power 3 by 2. 2 and 2 will cancel out. It will become 8 and this will become 125. 5 cube ka square root, which is 125. 8 upon 5 root 5. Okay, this is the ratio of initial to the final pressure. 8 upon 5 root 5. Okay, I hope you understand this. Now, this is it for today's class. Okay. In the next class, we will be discussing some new chapter. Till then, revise your concept. And if you have any kind of issue, any kind of problem, or any kind of doubt, you can connect to me. Now, thank you so much, guys. Bye.